Welcome, this is another Khan Academy support video. Here we're going to be taking a look at this week's last assignment, graphing linear relationship word problems. So congratulations on making it to the final assignment. Here you're going to see, much like assignment 4 now, the challenge becomes that these linear relationships have word problem, real world context to them. We're going to have to understand a story as part of making the graph. Or thinking about it in the other words, the graph is going to ultimately tell us a story. So here, for this assignment, each time they're going to give you a written description, a couple sentences that describe a linear relationship to you. And your job is going to be to make sense of that linear relationship that's described and use the data in that situation to build a graph. I'm going to pull up our notes from before to remind us that whenever we're working with linear equations, this y equals mx plus b is extremely helpful. If I know what the slope and the y-intercept is, then I can create a graph for any relationship that's linear or a constant rate relationship. The key again will be to read the word problem, so we're going to start with that. Quinn returned home one summer's day to find it sweat-inducingly hot. It's really hot when Quinn returns home. He turns the air conditioner on and fell asleep. The room's temperature decreased by half a degree Celsius each minute, and Quinn woke up 60 minutes later when it was 10 degrees Celsius. They ask us to create a graph where temperature will be marked on the y-axis, and x-axis will track the time in minutes since Quinn fell asleep. So again, it's key to understand what's going on here. Quinn turns on an air conditioner, falls asleep, so we're going to see a graph that should ultimately move down. We should see a negative slope to our graph here as Quinn's house cools while he's napping with the AC on. The y-intercept is where I often like to start. It's the beginning point. The challenge here is I read through, they tell me the room's temperature decreased by half a degree Celsius each minute. Anytime I see a speed, a rate, when they say per or each, I'm going to underline that in red because that's telling me about the rate of change or the speed. And in this case, this is going to be tied to our slope. Half a degree Celsius each minute the room's temperature goes down. I'm also told, and I'm going to put this in green, that Quinn woke up 60 minutes later when it was 10 degrees Celsius. And I actually want to change my mind. I'm not going to put that in green. I'm instead going to put it into purple. And the reason for that is this is describing us one point in time, but it's not the y-intercept point. They tell us Quinn wakes up 60 minutes later when it was 10 degrees Celsius. So one big challenge here is the word problem doesn't tell you the initial temperature in the room. It tells you the temperature after 60 minutes. So this is related to the y-intercept. It's one point that I can start with on my graph. It just might be a bit more challenging since they don't give me the y-intercept. I'm going to find that data point. If it says 60 minutes later and 10 degrees Celsius and the x-axis is measuring time, then I know that the coordinates for this data point are really 60 for x, or 60 minutes, and 10 degrees Celsius. I'm going to put 10 degrees there. So that's the first point that I'm going to plot on this graph from that purple data. The 60-minute mark, we better be at 10 degrees. I see this data point where my mouse is now and where I'm dragging that purple. This is the 60-minute, 10-degree data point that we needed right there. And now I also understand that the slope is decreasing by half a degree every minute. Or the slope is negative 1/2. I'm losing 1 degree every 2 minutes. So we're going to ultimately say, hey, we're losing 1 degree, and we're losing that 1 degree every 2 minutes. I'm going to recap what I just did there to get the slope. If it's half a degree each minute, then we're really losing 1 degree of temperature every 2 minutes. Half a degree each minute is the same thing as 1/2, or losing 1 degree each 2 minutes. And if I know that slope now, that can help me work back in time. Every 2 minutes I lose 1 degree. That means 60 minutes in time, I'm going to set up a proportional relationship. Oh, give me 1 second there. I'm going to try to figure out if I lose 1 degree every 2 minutes, and we traveled for 60 minutes, or in this case Quinn was sleeping for 60 minutes, I really want to know how many degrees go down every 60 minutes. And for me to figure that out, how many degrees do I lose every 60 minutes? I see that this needs to be multiplied by 30. 2 times 30 would be 60, so I can also multiply this by 30. I understand that losing 1 degree every 2 minutes is the same thing as losing 30 degrees every 60 minutes. And if I figured that out as my slope, as my speed, that tells me, hey, 60 minutes in, we lost 30 degrees, it's at 10 degrees. If I go back in time, it should have been 30 degrees warmer 60 minutes ago. And 30 degrees warmer would have been the 40 degree mark. So what I did there, I'm going to draw that out quickly. I went back in time. I knew if I'm losing 30 degrees every 60 minutes, if I'm going to travel 60 minutes in time, it better be 30 degrees cooler then. Or if I go back 60 minutes in time, it better be 30 degrees warmer. So it climbs up 10 degrees and left, or negative 60 minutes. Or I could say, hey, starting at this y-intercept here, if I go for 60 minutes, it goes from 40 degrees, it drops 30 degrees down to 10 degrees. I'm going to keep moving, taking a look at a couple more. Give me 1 second to clean up the notes from that old problem, get those out of the way. And now we can start reading here. So we're told that Wilbur landed his plane, causing it to descend at a rate of 2 kilometers per minute, and he reaches the ground after 15 minutes. Graph the relationship between the plane's elevation, which is height, how high it is in the air, relative to the ground, and the time in minutes. So here, we're going to have to make sense of, do we give a y-intercept, do we get a slope, how are we going to make the graph based on the context of this real-world problem? The first thing I see there, that Wilbur is descending at a rate of 0.2 of a kilometer per minute. I'm going to put that in red. The reason I'm putting it in red is because this is talking to me about a speed, a rate of change. You see the word rate and the word per in there, that tells me this is about slope. So here, if elevation is measured on the y-axis, we know for our pal Wilbur that the y is going to be measuring his speed of 0.2 kilometers. That's the y change. And it's going to take him every minute he loses 0.2 kilometers. It's a descent, that's why it's negative. So we're going to go ahead and set that ratio up right here. Losing 2 kilometers every 1 minute. So if he's losing 2 kilometers every 1 minute, we also need some more data points. It tells us he reached the ground after 15 minutes. And I'm going to put this in purple again. Reached the ground after 15 minutes. This is a specific 1 point in time for this relationship, but I chose not to put it in green because it doesn't happen to be the y-intercept. They're telling us after 15 minutes, he reaches the ground. If you reach the ground, you're really at an elevation of 0. So it says 15 minutes, that's really measured by the x-axis. And after 15 minutes, our height is 0 kilometers. So based on that, I'm going to go ahead and plot my first point. This told me he reached the ground after 15 minutes, so I'm going to take this graph, and I'm going to plot it right between 14 and 16 is where the 15-minute mark would be. So this point right here represents, hey, this is when he lands his plane. He's at 0 kilometers after 15 minutes. If the rate is 0.2 kilometers every 1 minute, I'm going to go ahead and take that 0.2 and I'm going to multiply by 15 minutes, because what I'm really curious about here is, hey, 15 minutes ago, how much height should he have had? Because he loses 0.2 kilometers every 1 minute. He got to the ground in 15 minutes. I want to know how much he lost in those 15 minutes. So I'm going to take that negative 0.2 and I'm going to multiply it with 15. If 2 times 15 is 30, then I know that, set up this ratio a little better first. So we're going to go to 15 minutes, and the question is, how many kilometers to get there. So if I multiplied the 0.2 by 15, 15 times 2 is 30, so 15 times 0.2 is just 3. Again, I'll show this quickly, I guess, on our calculator. 0.2 times 15 is going to equal exactly 3. But if I knew that 2 times 15 was 30, I could know 0.2 times 15 without a calculator. So that tells us, hey, we're going to gain or lose 3 kilometers every 15 minutes. That means 15 minutes ago, if he's on the ground, 15 minutes ago, he must have been at the 3 kilometer mark. Again, I know the y-intercept is a 3 kilometer height because it takes 15 minutes at this speed to drop 3 kilometers, and it took him 15 minutes to hit the ground or get to the ground. Hopefully that makes sense. Again, finding the purple here gave us one data point, and then the slope, the speed, helps us work back in time to where his elevation was at the start of this flight. I'm going to show one more example. These are certainly challenging, so if you're seeing different examples at home and you're a little bit stuck, I'd encourage you to use my process of reading through the word problem, trying to find the slope, trying to find any data points on the graph, but you can also email me if you're a little stuck, and I'm happy to jump onto Zoom. Okay, for our last one that we're going to take a look at, 1 second to clean up some of the notes from the last problem, and we're good to go. So Siraj takes a slice of pizza from the freezer and puts it in the oven. The oven heated the pizza at a rate of 7.5 degrees Celsius per minute, and it reached the desired temperature of 80 degrees Celsius after 12 minutes. Graph the relationship, and to make the graph, the pizza's temperature is going to be on this y-axis, and the time that the pizza is being heated for in minutes is being measured on our x-axis. So as I read through this, taking a pizza slice from the freezer, put it in the oven, our pizza, our graph, the blue line better move up. I'm making sense of that before I even start because the pizza is going to be heating up. The temperature is going to grow over time when I put it in the oven. I'm told that the oven heated the pizza at a rate of 7.5 degrees Celsius per minute. Whenever I'm seeing that language about rates, whenever I'm seeing the word per, I think about speed, slope, my rate of change. Here our rate of change is 7.5 degrees Celsius every 1 minute. So I'm going to go ahead and put that information in here. 7.5 degrees Celsius, and it's gaining, plus 7.5 degrees Celsius, and it's gaining that 7.5 degrees Celsius every 1 minute. So every time that pizza's in the oven for a minute, it's gaining 7.5 degrees of temperature. That's our slope. It's a key data point to know here. The other data point they give us, if they just tell you the slope but you don't know where the pizza starts at temperature, you can't make a graph. So they need to tell us something else about the relationship. They don't give us the y-intercept, the beginning temperature of the pizza. They continue to make these challenging by giving us a different point. So in purple, I'm going to underline this data. Not at the beginning, but after 12 minutes, we know the pizza has an 80 degrees Celsius temperature. X is measuring minutes, and I know, hey, at the 12-minute mark, so that's for my ordered pair, at the 12-minute mark, I know the pizza better be at 80 degrees. That's really what this data point here, or this sentence, is telling me. So I'm going to go ahead and graph that point. 12 minutes, I'm going to find an 80-degree pizza. Line up with the 12 minutes, move that up to 80 degrees, drop it there. Now that represents my 12-minute mark in an 80-degree pizza. And I also knew this pizza was gaining 7.5 degrees every minute. I'm at the end of the graph, so I kind of have to work back in time. And my question is, hey, if after 12 minutes it's at 80 degrees, I want to know how much temperature it gained at this speed. So I'm going to flip back to red. I'm going to switch this ratio, 7.5 over 1, a unit rate. I want to know how much the pizza gained in those 12 minutes. In other words, I need to multiply this ratio by 12. 7.5 times 12, which I'm going to use a calculator for, but you could do in lots of other ways. 7.5 times 12 gives us 90. So that tells me here that if I do 7.5 degrees every 1 minute, I gain 90 degrees. I gain 90 degrees every 12 minutes. And this may be a little confusing. You say, well, wait a minute, the pizza's only at 80 degrees. How did it gain 90 degrees in 12 minutes? Well, that's because if I do 80 minus those 90 degrees, temperature can hit negatives. This pizza was frozen. Celsius at 0 degrees is when you start being frozen, but it was in a cold freezer and it started out at negative 10 degrees Celsius, a little below the freezing point. And now this would show me, hey, if I took 12 minutes to heat that pizza up, it would gain those 90 degrees in those 12 minutes using the speed and get up to this 12-minute 80-degree point we should have. So again, finding a data point and then using slope to work back in time and find another data point, which turned out to be the y-intercept here. I hope this has been helpful. Number 4 and number 5 this week are certainly challenging, so if you're working on them, I would love to jump onto Zoom and help you work if you're a little stuck. If you're figuring these out on your own, super impressive work. Keep it up. Thanks for working to the end of the Khan Academy this week. Thanks for watching to the end of the video, and have a great day.